Every single day, you throw something away. A newspaper, a cardboard box, a paper bag from the grocery store, maybe a stack of old magazines you kept telling yourself you would read someday. You fold it, crush it, toss it into a bin, and forget about it completely. But that paper does not disappear. It goes somewhere. And what happens to it next is one of the most quietly extraordinary industrial transformations happening on Earth right now. Somewhere in a massive facility, a building so large it has its own internal weather system, its own fog, its own humidity clouds hanging near the ceiling, 500 tons of used paper arrives every single day. Old newspapers, cardboard packaging, office documents, magazines, all of it crumpled, dirty, used, and seemingly worthless. And inside that facility, every single ton of it is being reborn. Not recycled into something lower quality, not compressed into fuel pellets or landfill filler. Reborn into something you use in your most private moments every single day. Something you expect to be soft, clean, strong, and pure. How does filthy waste paper become premium toilet paper? How does yesterday's trash become tomorrow's most personal product? The answer involves chemistry, engineering, pressure, heat, and one of the most fascinating industrial processes most people have never seen or thought about for a single second. This is quiet tech process. The world has a paper problem, and it is enormous. Every year, human civilization produces over 400 million metric tons of paper and cardboard. That number is almost impossible to visualize. Stack it up and it would cover entire countries. Burn it and it would darken skies for weeks. Bury it and it would fill valleys. And most of it gets used once. A cardboard box ships a product across the country. It gets opened, tossed aside, and replaced by another cardboard box. A newspaper gets read on a Tuesday morning commute and ends up wet and torn on the floor of a train car. Office paper carries a memo from one desk to another and then sits in a recycling bin for 3 weeks before anyone deals with it. The average person in a developed country generates roughly 200 kilograms of paper waste every single year. That is the weight of a grown adult in discarded paper from one person in 12 months. Now multiply that by hundreds of millions of people. The landfill crisis this creates is staggering. Paper and cardboard account for roughly 2/4 of all solid waste in landfills across the United States alone. In Europe, the numbers are similar. In rapidly urbanizing parts of Asia and the Middle East, the paper waste problem is accelerating faster than waste management systems can keep up with. And here is the environmental tragedy hiding inside that statistic. Making paper from virgin wood pulp destroys forests. It consumes enormous quantities of fresh water. It requires massive amounts of energy. The chemical processes involved release pollutants into rivers and air. Every ton of virgin paper produced carries an environmental cost that compounds silently over decades. Meanwhile, perfectly usable paper fiber is sitting in landfills, rotting, releasing methane, contributing to groundwater contamination, and occupying land that cities desperately need. The fiber is already there. It has already been processed once. The energy to create it has already been spent. Throwing it away and then cutting down more trees to make new paper is not just wasteful, it is a kind of industrial madness. Someone had to find a better way. The idea of recycling paper is not new. People have been doing versions of it for centuries, long before the word recycling existed. In 17th century Japan, used paper was collected, repulped, and turned into new sheets. In Europe, during wartime paper shortages, every scrap was saved and reprocessed. But recycling paper at industrial scale, processing hundreds of tons of mixed, contaminated, multi-grade waste paper every single day and turning it into a premium consumer product, that is something else entirely. The challenge that engineers faced was not simply mechanical, it was chemical, biological, and psychological all at once. The mechanical challenge: how do you take paper that has been printed on, glued, laminated, stapled, wet, dried, compressed, and mixed with dozens of other paper types and reduce it back to clean, usable fiber? The chemical challenge: how do you remove ink, dye, bleach residue, food contamination, adhesives, and synthetic coatings from fiber that is microscopic in scale? And the psychological challenge: how do you convince consumers that a product made from waste paper is just as clean, just as soft, just as pure as one made from freshly cut trees? Engineers and manufacturers spent decades refining the answer. The process they developed is called de-inking and repulping, and when it works at full scale, it's one of the most elegant industrial transformations in modern manufacturing. It begins with collection. Waste paper arrives at the facility in enormous compressed bales. Each bale weighs several hundred kilograms and is tightly bound with steel wire. The bales come from municipal recycling programs, office collection schemes, commercial packaging operations, and print industry waste. Newspapers, corrugated cardboard, office white paper, magazines with glossy coatings, mixed grades tumbled together. The first machine to touch these bales is called a pulper. The pulper is essentially a giant industrial blender filled with warm water. The bales are dropped in, the steel wire is removed, and the machine begins to agitate the mixture at high speed. Within minutes, the fiber paper begins to separate from each other, breaking down from solid sheets into a wet, gray, soupy slurry called pulp. This pulp is perhaps 97% water and 3% fiber at this stage. It looks nothing like paper. It looks like dirty gray soup. But the fiber is in there, and now the real work begins. The pulp travels through a series of screens and filters designed to catch contaminants. Staples, plastic film, sand, glass particles, bits of metal. Anything that is not paper fiber gets separated out and sent elsewhere. The screens have different sizes at different stages, catching progressively smaller contaminants as the pulp moves through the system. Then comes the most critical stage of the entire process: de-inking. Ink particles are still clinging to the individual fibers at a microscopic level. Left in place, they would make the final paper gray and dull. To remove them, the pulp enters flotation cells, large tanks where air is pumped through the slurry in a continuous stream of fine bubbles. The ink particles, which are hydrophobic, meaning they naturally repel water, attach themselves to these air bubbles and float to the surface. The surface foam, heavy with captured ink, is skimmed off and removed. What remains in the tank is progressively cleaner, progressively whiter fiber. This process can be repeated multiple times for high-purity applications. For toilet paper production, where whiteness and cleanliness standards are extremely demanding, the pulp may pass through flotation de-inking several times. After de-inking, the pulp is cleaned further through centrifugal cleaning, spinning the slurry at high speed to separate any remaining heavy particles by density. Then it is bleached using carefully controlled chemical processes to achieve the brightness required for the final product. The resulting pulp at this stage is remarkably clean, white, soft, and composed of millions of individual cellulose fibers, the same building blocks as virgin wood pulp, now recovered from what was, hours ago, a dirty compressed bale of used newspaper. Now it must become paper again. The clean pulp is diluted even further and pumped onto a moving wire mesh screen called a forming fabric. The water drains away through the mesh almost immediately, and the fibers begin to bond to each other through a process called hydrogen bonding, the same natural chemical attraction that makes paper strong in the first place. The wet paper sheet then passes through a series of press rollers that squeeze out more water mechanically. It enters a massive heated cylinder called a Yankee dryer, a polished steel drum that can be several meters in diameter, heated internally with steam. The paper wraps around this drum, drying almost instantly, and as it peels off the Yankee dryer surface, a blade called a creping blade catches the paper and causes it to wrinkle microscopically. This creping process is what gives toilet paper its characteristic softness and stretch. Without it, the paper would be stiff and flat. With it, it becomes the gentle, flexible product that consumers expect. The finished paper is wound onto enormous parent reels, sometimes over 5 meters wide, then cut, perforated, and rolled into the familiar consumer product. The engineering of this process sounds clean and logical on paper. In practice, it is relentlessly difficult. Contamination is the constant enemy. Modern packaging uses paper combined with plastics, waxes, foils, and synthetic adhesives in combinations that are extremely hard to separate at the fiber level. Sticky adhesive particles, known in the industry simply as stickies, are perhaps the most persistent problem. They survive the pulping process, survive screening, and then reattach to equipment and paper surfaces at the worst moments possible, causing breaks in the paper sheet, damage to machinery, and costly downtime. Managing the chemistry of the de-inking process is also a continuous challenge. Different ink types, oil-based, water-based, UV-cured, laser toner, behave completely differently in the flotation system. A batch of paper that is heavily contaminated with laser-printed office documents requires different chemistry than a batch of newspaper. The system must be constantly monitored and adjusted. Water management is another enormous challenge. The process uses vast quantities of water, and modern facilities are engineered to recapture and recycle that water through closed-loop systems. But maintaining water quality through repeated recycling requires sophisticated treatment processes running continuously alongside the main line. And then there is the quality consistency challenge. Consumer expectations for toilet paper are surprisingly demanding. Softness, strength, absorbency, brightness, these must remain constant roll after roll, day after day, even as the input material varies wildly in quality and composition. When this process runs at full scale, the numbers become genuinely staggering. A single large recycled tissue facility processing 500 tons of waste paper per day keeps that paper out of landfills entirely. Over 1 year, that is over 180,000 tons of material diverted from burial. That is the equivalent of saving several thousand mature trees every single day when compared to virgin fiber production. Water consumption in modern recycled paper facilities is a fraction of what virgin pulp mills require. Energy consumption, while still significant, is substantially lower. The carbon footprint of recycled toilet paper production is measurably and meaningfully smaller than its virgin fiber equivalent. And the product that comes out the other end is by any objective measurement equal to, or in many cases better than toilet paper made from freshly cut trees. The fiber length, the softness, the absorbency, these qualities are preserved through the recycling process when the engineering is done correctly. What arrived as gray, compressed, dirty waste has become something clean, white, and genuinely useful. There is something quietly profound about this process. We live in a world that has trained itself to think of waste as an ending. You use something, it is finished, it goes away, and something new must be made to replace it. That linear thinking has driven resource consumption to levels the planet is struggling to absorb. But paper recycling at this scale is a demonstration of something different. It is a demonstration that the materials we throw away still contain value, still contain the fiber, the energy, the effort that went into making them in the first place. It is a demonstration that with the right engineering, the right chemistry, and the right industrial will, an ending can be turned into a beginning. 500 tons of trash every single day, reborn into something people reach for without a second thought. That is not just recycling. That is one of the quietest, most underappreciated acts of industrial transformation happening on Earth right now. And now you know exactly how it works. This is Quiet Tech Process.